So good morning everyone. This is E512 CMOS Analog IC Design, and today is September 22, 2023. So we are talking about current meter. So the simplest circuit which we have studied was as follows. Right? So from here we can measure the current, which is I0 and here I in, and some voltage is here VGS, right? So on the basis of this particular GM and all, we can determine the current, we can determine VGS, and we can also determine the VDS. Note that in this particular circuit, we need to see two things to evaluate whether this current source is a good current source or not. Those two things are, which are those two things? Output impedance and the output voltage. That is what we need ideally, but we need to check for this current mirror, right? That we need to do, that we need to evaluate. So what is the output impedance? R out. Let's call this one as M2 and this one as M1. O2. Although it's infinite, but you know that the value is around in kilo ohms, right? What about V out? VDS you are writing. These two things, we can keep it over here. By the way, this is not exactly VDS, but VDS set. What is the value of VDS set? Generally, like with our calculation, it has to be more than 250 millivolt. You wanted to have it 0, but it's not possible to have it 0. This is what you achieve with the current source used by the MOSFET circuit, which is using the current mirror. Let's see here. Right. One more thing we can see you. Okay, if you remember, I told you one more thing. Overdrive voltage. Overdrive voltage is also like VOV. Some people writing VOV, some people are writing VOD, and that's the voltage over here. Just to make sure that this particular, or sometimes people are writing VDS set. Right? So that V on voltage is equal to actually here VDS, and that's equal to VGS minus VDS. That also known to us, right? Now look at this particular circuit where we have M1 and M2. Let's go this way. If here it's VGS with respect to ground, that's known to us. Here it's VGS minus VTH, right? That is actually equal to VDS set. That is also equal to V overdrive voltage or VOD, whichever you want to use. Different books are following different things. Generally, like Behzad Razavi is using VDS set. In a case of Alan Holberg, he is using V on. Sometimes he is also using VOV. Anything you can use. I'm keeping VDS set. So all are different notations. But let's forget about this one. I know that value is more than 250 millivolt just to keep this transistor is in on condition. So if I am measuring from here to here, if it is VGS minus VTH, what voltage should be here between gate to drain? How much potential it has to be there? Simple KVL, follow that. So if this is VGS, look, these two are the same terminals. Potential cannot be changed. It's VGS minus VTH only. However, here VGS is there plus VGS. So how much is required over here? Minus VTH, right? So how to make minus VTH? You need to keep minus terminal here, plus terminal here, and let's call this one as VTH. Then I can see two voltage sources in series, which is making VGS minus VTH, right? So, and that's exactly equal to VDS set, and that has to be greater than 250 millivolt. It will come automatically. There is no problem in that, right? And our output impedance is equal to forgot to just 1 minute because exactly we want to do in single stage amplifier we wanted to achieve very high gain, right? This is what our gain is, our ultimate aim is. We want to have more and more gain. Common source amplifier we have seen, common gate amplifier we have seen, common drain we have seen. So common drain has less than 1 volt, 1 as gain. Common gate, of course, you can have more gain, but by looking at that you can find out the gain may not be very high, right? Maybe in the range of intrinsic gain only, right? CS and CG will have the gain which is in the range of the intrinsic gain of the transistor. Intrinsic gain is nothing but GMRO, right? So if you remember, if this is 100 ohm and this is 1 kilo, so it's around 10. Generally, this for bigger technology node, that is between 18 to 20 volt per volt. However, in case of smaller technology node, this goes very little, maybe 10 volt per volt or something like that, right? So I can achieve the gain of, let's say, 20 volt per volt. Let's assume that the base value, that is going to give me around 26 dB. I want higher gain than what we are achieving in common source or common gate amplifier, right? By the way, common gate amplifier is only useful when you want to give current as an input, right? Whereas in this case, voltage is already there, right? Or you can design an operational transconductance amplifier from here. So that's the thing. So we are going to choose common source amplifier, which will have higher gain. So what you can do, you can increase the output impedance to achieve very high gain. Increasing output impedance means that is what we were doing. So GM times output impedance. That's what generally the gain used to come, right, for the common source amplifier. So how to increase output impedance is what one technique is, go with the multi-stage. Okay, so if you are adding the multi-stage amplifier, common source after common source and common source after common source, that will give you the higher gain, right? So gain is getting multiplied every time, so that's possible. But the problem here is adding stages will decrease the bandwidth, right? The bandwidth is going to decrease, so I do not want a solution which is going to give reduction in the bandwidth. Bandwidth also have to be there. So by the way, just for all of you, if you are keeping stages multi-stage, input of one stage is connected with the output of the previous stage, then such structure is known as the cascaded structure, right? This is already known to you, I believe, right? You heard the word cascading of the stages, right? Next thing is, there is one more gain boosting technique. We'll learn it in different chapter when we are going to learn the differential amplifier. So let's not talk about it. But before going to that, I'm going to give one more technique just to find out the resistance measurement when such kind of circuit is there. Look at this. There is an NMOS. There is a resistance, value might be like Rs. Let's assume any value is there. And if you're looking from here, then what's going to happen? Can you find out that value? If you're looking from here, now technique won't work. You have to follow the equation. Write down the equation, like Vx is equal to whatever you want to write down. Just write down and find out what is the Rin you are seeing using the Thevenin theorem.
R naught plus Rs bracket 1 plus Gm into R.
You just write down. You find out.
Sorry.
Others should also get chance, right, to solve it. You can use a table. Srishti, now I remember. Sheikh. Okay, who is next? Next to Vishal. What's your name?
Sharad.
Sharad. Okay. I'll try to remember one better. What's your name? Ankit.
Ajay.
Ajay. And you?
Adarsh.
Hitesh. Okay. Is Palash is today here or Palash? No. So you can write down this equation, right? So that's Vx minus this potential. This potential is how much? Rs Ix, right? Keep it here. Divide by R0. Okay, R0 is this resistance. Okay, I made a mistake. No, R0 is this. Minus Gm Ix Rs is equal to I. Just to, for these two, it has been written, and I found out the current, right? So that is what we have done, and Vx by X is going to give you. What are you saying? You're saying something else, right?
Same, but Gm Rs into R.
Okay. R naught plus Rs is common and 1 plus Gm. That is what you are saying, huh? Right?
Gm into R.
Hmm?
Gm into R.
Why Gm into R? Yeah. Yeah. R naught is there, right? R naught is there. True. So the final answer which we got is as follows, right? So if there is a circuit which looks like this one, understand, if there is a circuit looks like this one, whatever voltage you are giving, no matter what voltage you are giving, you are looking from here, so at that time this will go to ground, by the way, whether it's V in, V bias, it doesn't matter, right? So I don't care about this voltage, just I care about one thing, that M1 has to be in saturation. If it is in saturation, then this particular small signal model holds, and that's going to give me Rin is equal to Rs plus R0 plus Rs times R0 times Gm, right? This is what, so that makes Rs plus R0, sorry, R0 plus Rs in common and 1 plus GMRO, right? Understand, GMRO is much higher value than 1 always, right? I can approximate these two, R0 plus Rs times Gm times RO. Of course, RO will be always, like if this is 1 kilo ohm, this is almost like 10, Rs is let's say 1 kilo or anything more than 1 kilo is going to be always much higher than the first term. I can approximate this to Rs times Gm times RO. We can do this, right? So always remember this and keep it somewhere in your mind, right? When we are going to use it very frequently, you know that looking from here, Rin is an approximated value of Rs times Gm RO. right? This is what we are going to see. No problem, right, in this one? Okay. So this is already there. Now let's. Okay. This is little bit. Okay. So let's find out RO if this is the case. What is RN here? Somebody can tell me? Shrishti. No answer is. If you want, you can use your notebook. Okay, let's go this way. Srishti. What is the resistance looking into this? How much is the resistance? Just now, a few minutes back, you were here or somewhere else? Use this. So tell me. Looking from here, it's not a simple transistor. If it is a simple transistor, there is no resistance, then RO is visible. Yeah, Gaurav? What is the RN here? This red colored circuit.
Sir, R0 into GM into RS.
GM1 times RO1 times RS. Right? Looking from here. Right? Use same thing and tell me what is their answer. Srishti. Two. Right? So it's very simple, right? Okay. Yeah, Amit. Now tell me, what is the answer? If this is the case.
GM2 R02 R01.
Okay. Yeah. Others.
So this multiplication into R01.
So tell me answer. Not
GM2
one.
into R01 into
GM2 into R0 1. Why R0 1?
Sorry.
R0 2. Okay. Then
Into this R01 into R03.
no, that's wrong answer. That's why it's not simple or simple multiplication. Nothing is like that. Yeah. That makes sense.
Addition.
Okay. एक मिनट रुको. Anybody? Abhishek? Okay. Another Abhishek. What's your answer? Abhishek, what answer you want to give? Same answer what Adarsh has given. So he is giving this answer. Okay, let's go this way. Let's make this particular question little bit simpler. What is the resistance looking from here? What is the resistance looking from here? There is nothing up. Let's forget about M2. Now tell me, Adarsh.
Sir, R02 into R03.
अरे भाई R0 है ही नहीं. There is
Sorry,
nothing.
R01.
Tell me the correct, full answer. Not R0. Look, when I okay means you people haven't. Abhishek, what do you think? Sorry. Narmit, Abhishek. What answer will be there if this circuit is only that much? There is no M2. If there is no M2, I removed it now. Just now Srishti gave the answer, right? What was the answer? Follow this and give me the answer. Now, Gaurav, what's the answer here?
Sir, GM1
Hmm.
into
RO1 times RO3, right? If this is the resistance, let's replace the whole thing with this resistance and name it as some RS. And if I keep here one more transistor, which is M1, now what resistance I should see? GM1 RO1 times RS, where RS is nothing but GM3 RO3 times RO2. You keep it here, so GM1 times RO1 times GM3 times RO3 times RO2. That's a simple multiplication, really simple multiplication, but you miss, right? Narmit, are you getting what's going on? Right? Okay, just for my satisfaction. Narmit, tell me what is the resistance looking from here?
GM1
Hmm?
into 1 by GM3
Okay,
into R0.
okay, very good. Okay, let's. Now tell me what is the resistance? This is V bias 1. Now what is the resistance? Narmit.
सर जो नीचे वाला पॉइंट
No, no, this give the answer. Why you're getting confused now.
है GM1
GM1
into R01
R01, very good.
into GM3
GM3
into 1 by GM2 into R0.
Look, you have to wait for the last transistor. Until that, all are intrinsic gain. That you have to multiply. Right? So, this is the intrinsic gain of this one. This is the intrinsic gain of this one. And the last resistance. Just keep that. That's the trick if you are not able to follow. Okay, let's go this way. Somebody wants to volunteer. What's your name? Yeah, Vinod. Vinod, tell me. What's the answer?
GM1 R1 GM2 R2 1 by GM4
But you forgot something. If there are branches, then it's going in parallel, right? So, if you're getting any problem, then you know break it in a small resistance values, right? Find out the resistance here, find out the resistance here, keep them in parallel. Means looking from here, then keep that value multiplied with the intrinsic gain of this one. So, GMRO1 times, let's call this one as RS. So what is the RS value? Maybe R1 and R2. GM2 RO2, why GM2 RO2? It is going, it's only RO2. It's only RO2. If I'm looking, forget about this one then. This part if you forgot, then looking from the drain of a transistor whose source is connected to ground is going to give you only and only RO2, right? Looking from here, again this becomes cascade. By the way, this particular, if you are stacking one transistor on top of it, that is known as the cascade. Do we have any Bengali here? No. Okay. Like I used to say this also every year to my students. When I used to study in Kharagpur, my professor was Bengali, so I used to think that he's talking about Cascade. But he's saying Cascade, but yeah, Cascade exists. Okay, it's separate thing. Right? So anyway, so now tell me. So this particular Cascade,
1 by GM4 into GM3 into R naught.
GM3 are not 3. Okay, so keep it here. So that gives us GMRO1 times RO2 in shunt with 1 by GM4 times GM3 RO3. Of course, if you want to approximate, you can approximate it to GM1 RO1 times RO2. That's possible because this particular branch has very high resistance, right? Compared to that one. It's multiplied with. So, if you want to approximate, you can approximate depending on GM4 GM3 ratio. If both are same, GM4 GM3 both are same, then RO2 in shunt with RO3 you can write down, no problem, right? That then you have to write down everything. Any problem with this one? Okay. Let's try this one then. Now tell me the resistance seeing from here. Who can volunteer? It's not difficult, right? It's very easy. इसको फिर हम लास्ट दिन ऐसे इसको यूज करोगे क्या? ये बहुत क्रिएटिव है मेरे लिए. That's why I want to know. I'm not stopping you to do that. You can do it, but it gives better remembering the things or what. Okay. Okay. Wherever you want to write, you can write down. Now, Aman, do you want to try? Take help from Gaurav. Gaurav has already solved the question, right? Hmm. The one who has the final answer. Vishal. एक मिनट रुक जाओ. Let's try with those people who are struggling, still not getting the answer. I believe you got the correct answer. Right? Gaurav, you got the correct answer. Okay. Narmit, Abhishek, going fast or are you able to follow? Just you have to see the cascade. If there are cascade, then GMRO1 and the resistance. That resistance you have to find out. Right? Sometimes if there are branches, you have to keep them in parallel. Okay. Let's start from here. Narmit, what is the resistance looking from here where there are two transistors are in parallel? So what will the final looking from here, this node, two transistors are in parallel, so
That is M5.
M3 and M4, so
R naught 3 is parallel to R naught 4.
no, this is diode connected.
1
1 by GM3 in shunt with RO4. You can approximate this to 1 by GM3 if you wish. Okay, looking from here where M2 and then two transistors are in shunt. What is the value?
GM2
GM2 RO2,
into that.
right? Looking from here, what is the value? GM5, Abhishek is saying something here. Times R1. So here you are seeing GM2 times RO2 times 1 by GM3 in shunt with GM5 times RO5 times R1. And looking from here, what is the value? R in GM1 RO1 times GM2 RO2 times 1 by GM3 in shunt with GM5 RO5 R1. Actually, there are many situations you will see where we are not going to solve the, that KCL, KVL will not apply, and we'll get this answer. Right? Please use it. So, if you want to have very high gain, so same is actually applicable if it is PMOS side. Okay, let's start with slowly start with the simpler one. What is the gain of this circuit? Amit, very quickly. What is the gain of this circuit? There is a common source, right? What is the gain of this circuit?
GM1, M1, GM1, I01, I03, I02.
What are you saying? Let's make, right? Minus GM1 times RO1 in shunt with RO2, right? Okay. You can, of course, you can write out. Then, follow my previous lecture, right? It's online already. Okay, so what is the output impedance? Asking you, what is the output impedance? Looking here.
R1.
This side RO1, upside
R2.
RO2. So RO1 in shunt with RO2, that's the output resistance. The technique says looking from here, input minus GM1 times RO1 in shunt with RO2. Okay. If I add one more transistor M3 with V bias 2, now tell me what is the the gain. Let's start with maybe what is the output resistance. This side still we know that it's RO1. What is going in shunt? Upside. We studied Cascade, right? Use Cascade theory, right? When two transistors are stacked with each other like this, either NMOS or PMOS doesn't matter. Look, this VDD is also ground because it's AC ground. So this also goes to ground only. Same theory. So this is GM2, RO2 and RO3. Instead of this, if it is like this, oh, what happened? It's crashed. What is the resistance looking upside? If it is M1, M2 and M3, this is GM1, RO1, GM2, RO2 and times RO3. If this is diode connected, then it's 1 by GM3. If it is a resistance, multiplied by resistance, right? These are very simple. This is the triple Cascade, by the way. If it is just like this, now tell me, what will be the gain? Let's call this one as M3. Right? But here note that this is just for solving the question. But if you are doing this in real amplifier, this won't work. You need one more transistor over here just to match both sides. Look, if I don't add the red colored M4 transistor over here, the problem is this is the answer. Means the gain is still remain GM3 times RO3 only, because RO3 is smaller than the whole quantity, which is like if this is 20 and if this is 20 volt per volt, sorry, 20, and if this is 1 kilo, this makes 400 kilo ohm in shunt with 1 kilo. So 1 kilo is the winning one. Then it's not a good idea to have like this. So you need to keep one more transistor below common source this input. So then what we are going to see? Then what's the answer? Now tell me. Now tell me. Am I going fast? Nandit, Abhishek? Okay. Then please give the answer.
Sir, both will have the
Don't talk in the abstract ways. Just give me the answer. The final answer. Looking into top side, what is the resistance?
sir,
Narmit.
GM1
GM1
into R01
into R01, R02. Very good. Looking bottom side, what is the resistance?
GM3
GM3.
into R03
Very good. Okay. Times
minus
GM1. That's the answer. Okay. Looking from here only. Always from here. Where you are applying the input, looking from that side only. Whatever the GM is coming, that's the input resistance you have to see. Right? So this is the answer. Now you improved a lot. Earlier it was 20 volt per volt, but here if like this is almost like you can say 20 kilo in shunt with 20 kilo. If I'm approximating both sides are if they are equal, then it will be 10 kilo. Earlier it was just 1 kilo. Right? So you improved by 10 times in this case. Right? So Cascade will give you higher gain. That's what I wanted to tell you.
Sir,
Hmm.
if GM would be sorry, अगर V in the 4 पर होता, the M4 पर होता तो
That doesn't. Okay, V in M4 पे होता. Solve it. You tell. You can give the answer to solve this. Okay. Keep it as like question in assignment number 1. Okay. You made this question. Might be same, might be different. Right? Might be in your exam also. Right. So first question made by, okay, I forgot it. Ajay. Yeah. Right. So find out. Okay. But exam is a open book, right? As we have already discussed, it is of 1 hour, right? And it will cover whatever we have studied till now. Right? Open book. So whatever solution you want to have, Lazad Razali, do you have a solution? Just send it to everyone. Alan Goldberg solution also. Okay. I have everything. If you want, I can give you in pen drive. Look, through my mail, I cannot send any pirated thing, right? Students can do that. I can't do it. Right. So if you want the solution also, like with solution you can come, no problem. Take the printout, be there. Okay. But whatever we have studied, same thing will be there. Right?
Sir, first half में होता है.
I don't know. I don't know the timings. It is as per the institute calendar and all. We need to see that.
So syllabus is still current in
till this point, like if you have lecture tomorrow, then whatever will be tomorrow, that will also cover. Right? Can we meet tomorrow?
So tomorrow is already exam.
Hmm? Which exam? Tomorrow is your starting of.
Devices.
the microelectronics.
No, no, but is it officially